All right. Thank you very much for the introduction and the invitation, and also for organizing this seminar series. My title is Nonlinear Stability of the Schwarzschild family, and this is upcoming work with Michalis Stefermus, Igor Rodniansky, and Martin Taylor. And since this is a broad audience, I'll try to be rather non-technical and still convey some of the main PDE and geometric ideas. So I'll start with about 3 or 4 slides of introduction to tell you a little bit about the Einstein equations and about black holes, so that I can set up the black hole stability problem. And then in the second part, I state an informal version of the main theorem concerning the nonlinear stability of the Schwarzschild spacetime. And well, after some discussion of this theorem, the main part of the talk will be the third. So I'll discuss some ingredients of the proof and some of the ideas. And there the split is that I'll distinguish between linear difficulties, which were resolved in earlier work with Stefermus and Rodniansky on the linear stability of the Schwarzschild spacetime, and say a few things also about the the nonlinear difficulties that one has to address if one wants to upgrade the linear result to a nonlinear one. Okay, so let's start with the introduction. So the dynamical object in general relativity is a Lorentzian manifold Mg, and the governing equation is the vacuum Einstein equations, which state that the Ricci of this metric G is equal to 0. Now, what is the type of this equation? Of course, it's a tensorial equation, doesn't make reference to any specific set of coordinates. But if you write it in the right coordinates, so-called harmonic coordinates, you'll see that the equations become a system of quasi-linear wave equations for the metric components, with derivatives on the right-hand side, which are quadratic in derivatives of G. So since this is a system of wave equations, you expect there to be an initial value problem where you specify the metric and the first time derivative, and the geometric formulation of this is as follows: that you start with a Riemannian manifold sigma h and a symmetric 2 tensor k, which have to satisfy certain constraint equations, and then from this triple you can construct a 4-dimensional Lorentzian manifold Mg, which satisfies the vacuum Einstein equations. I should also mention the characteristic problem where you don't specify initial data on a space-like slice. So maybe I should say this as well. So the manifold that you construct here has, so sigma embeds as a space-like slice with metric h and second fundamental form k into this 4-dimensional manifold. But you can also specify initial data on 2 intersecting null hypersurfaces and study the characteristic problem, which is what we will refer to a bit later. Right, and this geometric initial value formulation can really not be overemphasized, because it allows us to talk about dynamics and in particular stability of solutions to the Einstein equations. The last bit of introduction about the Einstein equations that I wanted to give you was to say something about explicit solutions. Well, one explicit solution is certainly flat space. And the next non-trivial family of solutions is a black hole family, the so-called Schwarzschild family of black holes. And since it plays such a fundamental role in this talk, despite the fact that I only have 45 minutes, I'll spend 5 minutes explaining to you a little bit about the geometry of it, and in particular giving you some intuition of what a black hole is, which you can study very well with this particular example. So I've given you the line element of the Schwarzschild metric here in the original coordinates that Schwarzschild wrote it down to, and there are a couple of things that we can immediately see from the line element. For instance, that the metric is spherically symmetric. This is just the metric of the round unit sphere, that it's static, so d by dt is a Killing field, and also that it's asymptotically flat. So as we send r to infinity, we see that we recover the metric, the flat metric, written in polar coordinates. But why is this metric, or why does this metric describe a black hole? Well, it took several decades for people to appreciate this. So let's try to explain this. The best is to explain this in the language of Penrose diagrams. So I've drawn the Penrose diagram of Schwarzschild here. So let me explain how this diagram arises. So we forget about the spherically symmetric part of the manifold. So we quotient it out. We obtain a 1 + 1 dimensional Lorentzian manifold. And then we conformally map this 1 + 1 dimensional Lorentzian manifold to a bounded set in R1 + 1, equipped with its usual causal structure. So every point in this diagram corresponds to a two-sphere upstairs. And from every point, you can draw the future light cone and the past light cone as if you were in R1 + 1 in the plane. So you can easily assess what's in your causal future or in your causal past from the diagram. So why is it called the black hole? Again, well, I want to draw your attention to two subsets in this diagram. So remember, because we've done a conformal transformation, the asymptotic ends, the asymptotic infinities of the manifolds get mapped to boundaries of this set. So I want to draw your attention to this set here, which is called null infinity, which is a null boundary to the set where R is equal to infinity. So that corresponds to asymptotic observers at infinity in the flat region. And then there's another null hypersurface here at R = 2m, which for reasons that will become obvious in 10 seconds is called a horizon, because you see now, if you combine the things that I've said, that well, if you look at the point here on the in this region of the diagram, and you look at the causal future of this point, you see that this observer here can in particular communicate with observers sitting at infinity in this region, while if you look at an observer who has crossed this event horizon, and you look at the causal future, you see that this observer can no longer communicate with observers at infinity. So he's fallen into the black hole. So when you hear black hole, what you should have in mind is this notion of future null infinity of a set of asymptotic observers at infinity, and a horizon, an event horizon, which separates the region of space-time where you can communicate with asymptotic observers from the region where you cannot. Okay, so that's Schwarzschild. Now I have to say one word also about the Kerr family, which is a larger family, a two-parameter family, which contains the Schwarzschild family if you set the parameter A = 0. So A is the angular momentum per unit mass, and this describes a rotating black hole solution. It's also explicit, was found in 1963, so much later. And it plays a fundamental role in general relativity. It's believed to be the unique asymptotically flat stationary black hole solution. So it plays a fundamental role as an equilibrium or end state of gravitational collapse. So with all this being said, we can set up the black hole stability problem. Again, for those who are familiar with causality and the jargon, you can read the 4 lines. I'm just going to, again, explain it pictorially. So you want to look at a space-like slice arising from perturbations of sub-extremal Kerr initial data. You want to look at the maximum development of this initial data set. And then the claim is that your maximum development will have a subset which contains this notion of future null infinity and a regular event horizon, and which is moreover such that on the black hole exterior you converge to another member of the Kerr family with slightly different parameters of mass and angular momentum per unit mass. And here I've drawn the same picture with data being imposed on characteristic hypersurfaces, which you should think of as not making any difference. Okay, so that's the stability problem. Now, 2 remarks. So when I say stability, I always mean stability of the black hole exterior, and decay estimates are established on the black hole exterior. The interior is a completely different story. It's very interesting, and a lot of progress has recently been made on this, on studying the stability of the singularities in the interior. But again, nothing about this in this talk. And the second remark is that from what I've said, it's already clear that nonlinear stability of Schwarzschild cannot be expected to hold for all data, because even if you start with Schwarzschild, if you perturb it slightly, you expect to converge to a member of the Kerr family with small angular momentum, not to a Schwarzschild solution. But as we shall see on the next slide, we can prove it for a finite codimension set of initial data near Schwarzschild. And that brings me to the main theorem. So let's go through the statement, and then again I'll explain the pictures below. So we start from characteristic initial data, which are assumed to be sufficiently close to Schwarzschild of mass M initial, and lying on the codimension 3 submanifold of the moduli space of initial data. So let's even ignore that parenthesis for the moment. Then we look at the maximum Cauchy development of this initial data, and it contains a region R, which is this region here, enclosed by the horizon and future null infinity, which can be covered by a teleologically normalized global double null foliation, and which possesses a complete future null infinity, such that if you look at the causal past of it, you obtain this set, this set R, and the future boundary of R is this event horizon H plus. And moreover, if you look at the exterior, if you look at R, you remain close to Schwarzschild on R, and as you go towards the future, you asymptote inverse polynomially to a Schwarzschild metric with mass approximately the initial mass. So now let's talk about this lying on a codimension 3 manifold of the moduli space of initial data. And for this, let's look at this picture here on the left. So let's look at the space of all of initial data. And in this space, let's look at the ball of radius epsilon of data of Schwarzschild of mass mi. So the ball of radius epsilon around Schwarzschild data of mass mi. So what we expect is that for sufficiently small epsilon, all these data sets will converge to a member of the Kerr family. And you have to be, of course, very lucky in order to pick a data set that converges to Schwarzschild. And what's shown in the theorem is that through every point in this ball, there runs a 3-parameter family, which is such that on this 3-parameter family, there is a point such that the initial data corresponding to this point converges to Schwarzschild of mass MF. So you have to move along this 3-parameter family in order to ensure that you're converging to Schwarzschild. Okay, so that's the statement. Now let me say a few words about previous work. Of course, the first question that you might ask is, can I study this problem in spherical symmetry? And the answer is you cannot, because of something called Birkhoff's theorem, which says that there is no dynamics of the vacuum equations in spherical symmetry. But you can add matter, and the one of the simplest matter model is that of the scalar field. And this is what Decoupled and Rodniansky did in 2005 when they proved Price's law. So they actually proved large data results, but their results in particular imply that Schwarzschild is stable within the spherically symmetric Einstein scalar field system. And if you don't like matter and you want vacuum, you can also evade this Birkhoff's theorem by going to higher dimensions. You can look at the 5-dimensional class of biaxial Bianchi-9 vacuum spacetimes. And this is something I did in my PhD, and show that 5-dimensional Schwarzschild is stable within the class of biaxial Bianchi-9 symmetric perturbations. Now, what both of these toy models have in common is that they reduce to 1 + 1-dimensional system of PDEs, and the fact that you have spherical symmetry and the black hole actually breaks the supercriticality of the equations and make a big simplification of the problem. So different from this is the impressive recent work of Kleinerman and Scheftel, which concerns axisymmetric polarized perturbations, and shows the stability of Schwarzschild with respect to these perturbations. So here the axisymmetry helps because in axisymmetry, angular momentum is not radiated. So if you start from initial data which have 0 angular momentum, you also have 0 angular momentum in the future, and this can ensure convergence to Schwarzschild. And finally, I also want to mention, mention the related work of Hinz and Vargy, which concerns the case of a positive cosmological constant, where they proved nonlinear stability of slowly rotating current de Sitter spacetimes. Okay, so that brings me to the third part of the talk. We've done the introduction, and I've stated for you the main theorem. So now let's talk a little bit about the proof. And in order to appreciate the strategy of the proof, I want to remind you of well, one of the landmark results that we have on nonlinear stability for the Einstein equations, which is the stability of Minkowski space, and well, approach the problem from there. Now, there are essentially two main approaches that you can take. Maybe let's start with the second one, which is the one that's more direct from what I've already said, which is the approach of Lindblad and Rodniansky. You can work in harmonic gauge and try to estimate metric coefficients directly. So you think of the metric as being a small perturbation of the Minkowski metric. You derive a quasi-linear system of equations for the perturbation H, and you hope to prove a small data global existence result for this set of equations. So typically you need a null structure for this, and this is not present in this formulation of the equations. There's only something called the weak null structure, but this is certainly an approach that you can take, and that works, and that has successfully been done. The original approach of Christodoulou and Kleinerman to the stability of Minkowski space is different, though. There you forget about estimating metric components, and you do something that's perhaps a bit more geometric. So you estimate curvature components. So you estimate the Weyl curvature, it's equal to the Riemann curvature because we're Ricci flat, and the connection coefficients. So the analytical character of the Einstein equations is encoded in these two equations. You have a Bianchi equation for the curvature, and you have a system of transport equation for the connection coefficients. So that's the system that Christodoulou and Kleinerman study, and that's also the approach that we want to take when we go to Schwarzschild. Just one sentence. I mean, stability of Minkowski space is still an active area of research. You can couple to various matter models. You can ask questions about regularity and rates of convergence and things like that. So people are working on this. So what are the key ingredients in the original Christodoulou-Kleinerman proof of the stability of Minkowski space? Well, so if you want to prove a stability result, you might first want to linearize the equations. So let's formally linearize this Bianchi equation for the curvature. So we have the flat connection plus first order perturbation of the connection, and background curvature plus linearized curvature. We only keep terms to linear order, and because the background curvature is equal to 0 for flat space, we see that the first linearized equation is actually a decoupled equation for the linearized curvature. So the linearized gammas don't enter the equation for the curvature. So in linear theory, you can do a two-step procedure. You first prove estimates for the curvature components, which Christodoulou and Kleinerman did in a paper in 1990, and then you can go with the estimates that you have on the curvature to estimate the connection coefficients. Okay, that's good. But one thing that you already see from this is that because the connection coefficients are obtained via transport equations, you are forced into imposing a future normalized gauge if you want to see all curvature components and all of the linearized connection coefficients to decay. So you see this from this simple picture. So suppose you've done the estimates for curvature, you know now that curvature decays. Well, if you now estimate things from the transport equations and you integrate from initial data towards the future, well, you're never going to show that the gamma is going to 0, because when you integrate the transport equation, you're always picking up the initial data term, which is size epsilon. So the resolution of this is that you have to choose your coordinates wisely, such that your future hypersurface is chosen in a way such that the Christoffel symbols, or those Christoffel symbols that you want to estimate with the transport equations, are 0 on that particular hypersurface, because then you can integrate from the future towards the past, and you can show with the estimates on the curvature that actually also the gammas converge to 0. The drawback of this is, of course, that now you have two coordinate systems, one future normalized coordinate system and one initial data normalized coordinate system. So in particular, if you look at what the t prime equals 0, what the t equals constant, t equals 0 hypersurface is in the future normalized coordinate system, it will be different from the original hypersurface t equals 0 where you impose the data. So in other words, you're forced into estimating the relation between the two coordinate systems that you have introduced. So that's sort of the payback that you have for estimating something more geometric, namely the curvature, that you need this future normalized gauge. Then the third point I want to make about stability of Minkowski is the existence of the null condition, which is exhibited in the nonlinear terms in the gauge that Christodoulou and Kleinemann use. So that's nice. And finally, that in the case of Minkowski, there's a nice geometric characterization of Minkowski space, namely that if the curvature is 0, you know that you're in flat space. Okay, so now let's see what happens if we try to follow a similar approach for Schwarzschild. Well, the first and perhaps the biggest obstacle is that you look at the linearized problem, and now you no longer see decoupling. I mean, that's very obvious if you look at this. Now the background curvature, of course, Schwarzschild is not flat, so the background curvature is non-zero. So you'll see a term where the background curvature contracts with the linearized connection coefficient. So your first equation is no longer decoupled. And the big question is, how do you prove estimates for this coupled system now? The necessity of the future normalized gauge and the comparison and so on, that will be the same because we're still using the approach via transport equations. The null condition exhibited in the nonlinear terms, well, we have some hope that this will be very similar, because that's an issue about the wave zone. So that's far away. So that should be similar to what happens for Minkowski space. And the other thing that changes fundamentally is that we don't have a good characterization of the final state that we're converging to. Moreover, we don't know what Schwarzschild exactly we're converging to. So the final state is not known, and that's what forces us into this modulation theory that you saw on in the statement of the main theorem. Okay, so now my goal is twofold. I want to explain to you how to obtain estimates for this linearized system, and I want to make you appreciate the issue of the necessity of the future normalized gauge, and how I said this can already be appreciated in the linear context, how you see this future normalized gauge coming up even in the linear problem, and in what form. Okay, so let's talk about the linear stability then. So here we have the following theorem. So we look at the solutions to the linearized vacuum Einstein equations around Schwarzschild, arising from regular asymptotically flat initial data. And the theorem states that these solutions remain uniformly bounded on the exterior and decay inverse polynomially through a suitable foliation to a standard linearized Kerr solution after adding a pure gauge solution, which can itself be estimated by the size of the data. So I'll explain all the statements that appear in this theorem as we go along. You should already think that somehow this aspect of having to add a pure gauge solution in order to see decay is related to having to impose a future normalized gauge, which at the linear level will be what we'll call a pure gauge solution, but we'll get there. And in particular, the theorem tells you that there exists a codimension 3 subspace of data for which all solutions approach a linearized Schwarzschild metric. So this is in parallel with the theorem that I showed you before. Okay, so before we discuss this, the proof of this theorem 2, the linear theorem, let me just flash a slide with related work. So this has been a very active area. So first comment I want to make is that you can also do this Lindblad-Rodniansky type approach where you work in harmonic gauge in the linear context. So this has been done by Thomas Johnson, and there's also work by the group at Columbia, and it has been generalized to Einstein-Maxwell by Elena Georgi. Then you can ask what happens as you go to Kerr. As we'll see, a main part of the proof is the analysis of the Tucholsky equation. So this has been generalized to slowly rotating Kerr spacetimes. And there has also been progress on the linear stability of the Kerr spacetimes, so paper by Anderson, Bechdel, Blue, and Ma, and recently Hefner, Hinz, and Vargy proving linear stability of Kerr, very slowly rotating case. Okay, so now let's talk about the linear theorem. So first, we have to decide on how we want to linearize the Einstein equations, and for this, we want to pick a well-posed gauge, write the Einstein equations in a well-posed gauge, and then linearize them, and then try to estimate the linear system. Now, how do we do this? Well, we work in a so-called double null gauge. So we fix the Eddington-Finkelstein differential structure of Schwarzschild and consider a one-parameter family of Lorentzian metrics expressed in double null coordinates. So you see here this metric u equals constant and v equals constant are null hypersurfaces, and they intersect in topological spheres with metric g slash. So g slash, omega, the conformal factor, and b, the shift vector, are the dynamical quantities in the metric. And as epsilon is equal to 0, we obtain the Schwarzschild metric in the Eddington-Finkelstein coordinates. So any metric can be any metric can locally be put into this form. And I should also say that this double null gauge has been very useful in the analysis of the Einstein vacuum equations in various contexts, starting with Kleinemann-Nicolau, with Christodoulou in the formation of black holes, Luc Dafermos in the context of black hole interiors, and so on and so forth. So it's sort of natural to use it here as well. So we have now this one parameter family of metrics. Associated with this metric, we have a double null a null frame. E3 and E4 are null vectors. EA are vectors tangential to the spheres. And now our procedure is as follows: we compute all the connection coefficients gamma and all the curvature components R. We decompose it with respect to that null frame, and then we write down the equations that we obtain, and we linearize these equations. So for instance, the connection coefficients chi, which is defined like this, is the second fundamental form of the spheres in the null cones, in the outgoing null cones. We constructed the trace and the trace-free part, and then we expand let's say the trace so there's a Schwarzschild part, and there's a linearized part, so which we denote with a superscript 1, and they of course order epsilon squared terms. So that's our linearization procedure. Same you can do for the curvature component. So you decompose the Weil curvature with respect to these null directions. You get alpha, alpha bar, beta, beta bar, rho, sigma. I mean, it's not too important. And again, the linearized quantities will be denoted by a 1 superscript. And because Schwarzschild is so symmetric and special, there's only one of these curvature components, which is actually non-vanishing in Schwarzschild. Okay, so now, as I said, you write down these linearized Bianchi and linearized null structure equations. You get a well-posed system of equations, and you can try to do estimates on it. So I haven't, and I'm not going to write down this system because it would just take 3 pages and not give you too much insight, but I want to tell you how you do analysis for this system. So there are three main aspects of the analysis. The first is the pure gauge solutions, or what we call pure gauge solutions. So what are those? So these are solutions which correspond to infinitesimal diffeomorphisms which preserve the double null form of the metric. So what does that mean? Well, imagine we do a coordinate transformation. So we send u to u plus epsilon times some function of u v theta, same for v and theta. And then we can ask, how does the double null form of the metric change under this coordinate transformation? And you can single out a subclass of f's which preserves this double null form of the metric. So omega, of course, and g slash and b are going to change to order epsilon, but the form of the metric is going to be preserved. And then you can read off how omega, g slash, and b change to order epsilon and compute all the geometric quantities. And this is a solution of this huge linearized system. And this is naturally called the pure gauge solution because it corresponds to doing a diffeomorphism in the nonlinear theory. So it's just a coordinate transformation. So just to give you a sample lemma, so you can do this actually explicitly, and I've prepared one lemma here. So for instance, for any smooth function f of the coordinates v, theta, and phi, you can construct a pure gauge solution of this system. So you have values for linearized omega, linearized Christoffel symbols, linearized curvature expressed in terms of f and derivatives of f. So you can construct pure gauge solutions from functions f. And now you can already see the relation of this with normalizing your gauge to the future. So imagine I have a solution already of my system of gravitational perturbations. And let's say on the horizon, on this outgoing null hypersurface, I have a particular value of this component omega 1. Well, then I can try to solve that equation for f such that I obtain minus the value of omega linearized on the horizon. And then if I add this pure gauge solution to the solution that I already have, then the new solution will have the property that this metric coefficient will be 0 on the, let's say, the event horizon or the outgoing null hypersurface. So I can use these pure gauge solutions in order to achieve that certain Ricci coefficients or metric coefficients are 0 on particular hypersurfaces. And that exactly relates to what I said at the beginning of the talk about normalizing your gauge to the future. So the second important property of this linearized system are the linearized Kerr solutions. So you can write the Kerr family in double null form and linearize in the angular momentum parameter, and then you can read off again a 3-parameter family of explicit solutions to your linearized system, which correspond to the fact that Schwarzschild sits as a 1-parameter family within the Kerr family. Okay, so these are sort of important aspects. Now the real analysis starts with the analysis of the Tucholsky equation. So you have this huge system, but it is possible to derive a decoupled wave equation for 2 of these linearized curvature components, alpha and alpha bar. So they satisfy decoupled wave equations, and moreover, they're gauge invariant in linear theory. So anything that we've done here in any of these pure gauge solutions will have alpha and alpha bar 0. So they're not affected by this in linear theory. And moreover, alpha and alpha bar, you should think of that if you can estimate those, you really have caught the dynamical content of the theory, because you can show that if alpha and alpha bar are 0 and you're asymptotically flat, the only solution to your linearized system is pure gauge solutions plus linearized Kerr solutions. So in this sense, alpha and alpha bar capture the dynamical content of the theory. So let's try to estimate them. Now, alpha and alpha bar satisfy decoupled wave equations. However, you should think of these wave equations as being wave equations with the first order term, and this first order term prevents you from proving from having energy conservation or proving an integrated local energy decay estimate. So you're really in trouble if you're trying to estimate this equation directly. But there is a solution to this, and this solution is sort of inspired by the physics literature, by the transformation theory of Chandrasekhar at the level of mode solutions, which you can apply in physical space. And what you do is, so let's just discuss alpha. Alpha bar is very similar. Is you apply a certain second order operator to your solution alpha. So nabla 3 is a derivative in the ingoing null direction. So we just think d by du, let's say, in the Eddington-Finkelstein coordinates. And you construct this new quantity P out of alpha, and then you look at the wave equation satisfied by this quantity P. And what you miraculously discover is that P satisfies a wave equation without a first order term, a wave equation of this type. And this equation, so it's remarkable that you don't see alpha in this equation, obviously. And this equation does admit a good energy estimate and an integrated local energy decay estimate. So we're relying here on progress that has been made on the wave equation, the scalar wave equation on black hole spacetime. So I won't have time to get into that, but this has been resolved for the full range of angular momentum parameters on Kerr by Decoupled, Rodniansky, and Schlapp-Rothman. So we rely on this. We can prove good estimates for P, and then we can use a hierarchy of transport equations to prove estimates on alpha itself from the estimates on P. Okay, so now that we have estimates on alpha and alpha bar, as I said, we know that they sort of capture the dynamical content of the theory. But of course, from the analytical point of view, we need quantitative estimates for all geometric quantities, and this can be done. I've written 1, 2, and 3 for experts, which are familiar for this. So for the others, I'm just going to say that essentially what you do is you go through this huge system that you have, and you hierarchically estimate all the other curvature components and Ricci coefficients in a certain order, using the fact that you have good estimates for alpha and alpha bar. And there are various geometric features of black holes that go by the name of redshift and trapping that sort of come into your way while you're doing this, but this can be done. And what's again remarkable, and what by now we can explain, is that so your solution does not decay to 0. Not all quantities decay to 0, but you can only prove boundedness. And the reason is that you decay to a pure gauge solution, which is dynamically determined and can be quantitatively estimated from data. So again, what this means is, so you look at the solution from initial data, you prove boundedness, and then you do exactly what I said earlier. You look at this quantity omega on the event horizon, and you add a pure gauge solution, which makes this omega 0 on the event horizon. And then you can, in the new for the new solution, you can integrate backwards from the event horizon to show that the solution actually decays. Okay. So maybe let me skip the summary of the linear stability and go straight into the saying a few words about the nonlinear difficulties. So what are the main difficulties that you have to address if you want to upgrade this result to a nonlinear result? Well, one is again the choice of gauge. Then, well, the control of the nonlinearities. How do you modulate the angular momentum parameters to ensure convergence to Schwarzschild, and then the coupling of the above. So let me talk a little bit about the choice of gauge first of all. So we already know from the linear problem that if we want to see decay, our gauge has to be future normalized. But of course, now we can no longer just add pure gauge solutions, but we actually have to find null hypersurfaces which have certain properties concerning the Ricci coefficients and so on. So what's remarkable is that you have to normalize the the gauge both with respect to a future outgoing and an ingoing hypersurface. So in the linear theory, I told you that you add this pure gauge solutions, which normalizes the solution with respect to the event horizon. So in the nonlinear problem, you actually have to normalize your solution both with respect to the future outgoing hypersurface and also the ingoing hypersurface, which you can think of as being null infinity. So you also have to normalize your solution with respect to infinity, precisely because of this coupling with the nonlinear error terms, that normalizing your solution with respect to infinity ensures that certain quantities exhibit better decay near infinity, and you need this better decay to control the nonlinear error terms that you see in the equation. Okay, so I have two slides sort of with an overview of the proof of the theorem. So let me go through it. So how do we start? So we start with a 3-parameter family of initial data. So we look at our initial data and we add a sum of these linearized Kerr solutions. So we have a 3-parameter family, and then the proof will proceed by a large bootstrap, and our bootstrap region will look exactly like this. So we have the initial data specified on these blue hypersurfaces here, and we look at the latest UF, or the largest U equals UF, such that certain bootstrap assumptions hold in this region R UF. And again, the region is normalized with respect to these null hypersurfaces. Okay, so your bootstrap region is to assume that certain bootstrap assumptions hold in this region on the connection coefficients and curvature components, and moreover, you want to look at, so how does the modulation theory come in? You look at this sphere and you look at the angular momentum parameters on this sphere. So let's just think of one parameter for now instead of 3 for the rest of the discussion. So you look at the angular momentum parameter on this sphere here, and part of your bootstrap assumption is that as you run through your 1-parameter family of initial data, this angular momentum quantity r to the 5 curl beta should run precisely through the interval minus epsilon over UF. So that's the bootstrap assumptions, and then you need to improve them. So how do you do this? Well, you do what you did in the linear case. So you now first look at alpha and alpha bar, which now satisfy nonlinear wave equations, so nonlinear version of the Tucholsky and Reggie-Wheeler equation. So you obtain estimates. You have to estimate the nonlinear errors. You use the bootstrap assumptions, and you exploit the fact that they exhibit the null conditions in the gauge that you're using. And of course, as I said in the beginning of the talk, you have to relate now these two coordinate systems, the one which is normalized with respect to the future null hypersurfaces and the one which is normalized with respect to the initial data null hypersurfaces. So then you estimate the Ricci coefficients via these transport equations and the fact that you've normalized the gauge towards the future. And then you extend the solution past this U equals UF hypersurface, and then of course you have to show you have to construct a new sphere and new null hypersurface which satisfy the gauge conditions on these spheres, and moreover you have to check that the angular momentum parameter, if you look at the new sphere now as you run through a restriction of your 3-parameter family or 1-parameter family of initial data, exhausts the interval minus epsilon over UF plus delta, epsilon over UF plus delta, if you've extended from UF to UF plus delta. And there's a small computation that you can do that shows you that this should work. And then in this way, you conclude that UF is equal to infinity, and you conclude that that eventually UF is the event horizon. And well, I've swept a lot of things under the rug here, obviously. So actually, you need 2 double null foliations and in the near and the far region, and you also need to estimate the diffeomorphisms between the 2 different foliations and so on. But in view of the time, I'm just going to stop here and thank you.